Okay, let's get started. Your next assignment, homework 11, is related to hydraulic jumps and momentum and rapidly varying flow. So that one's due on Monday. We're going to continue talking about hydraulic jumps today. Before we do, though, I wanted to offer kind of some generalized observations related to the project. And one is related to the demand estimation hand calculations. And I noticed that some of you are scanning your hand calculations as color images. And I wanted to point out that when you do that, just inherently the scanning tools aren't able to generate as high quality an image if it is in color than if it's black and white. So you can see that if you're taking a picture of your paper and it's in color, I think maybe it's using a higher amount of compression because it's a colorized image compared to if it's black and white, then it's able to do it at a higher resolution, and then the fact that it's just got two colors means it can increase the contrast. And so just please, when you do your revised hand calculations, please make sure that your images are PDF scans and not just a picture that you've pasted into Word, because the PDF scanning tools that you use, they're able to correct for things like keystoning, which is when you take a picture of the page at an angle. Even if it's just a little bit of an angle, then the image is what's called keystoned. And so like Adobe Scanner or Cam Scanner, they both have image correction, and you can, in the settings, configure it to be black and white or grayscale. So if you're not sure how to do that, if you can't figure it out, stop by my office and I'll show you how you can improve your scanning quality for hand calculations. The other issue is some people were taking a screenshot of their system map, and instead of doing that, you should print to PDF from directly within WaterGems. And the reason why is, I think, similar to the other issue. It's just more clear that way. If you print to a PDF file from within WaterGems, then what it does is it creates what's called a vector drawing. And a vector drawing is where you could continue to zoom in infinitely, and the text is as sharp at whatever viewing level, whether you're zoomed out or zoomed in. The lines are all sharp, the text is sharp, whereas when you take a screenshot, it's just a series of pixels rather than an actual line. It's known as a scalar image when you take a screenshot, and so if you zoom in, then it just becomes blurry and pixelated, and sometimes it's tough to see all of the annotations that way. So please print directly to PDF, and it doesn't matter if the image is, well, if the network is only a portion of the page, I can still zoom in and see what I need. You could get it to be more of the page if you print like landscape instead of portrait. That's like another way to kind of maximize the real estate, is to use landscape orientation. But the main thing is don't just do a screenshot of your project map. So any questions about either of these requests? Okay, so you've submitted the reservoir sizing. Those are generally the easiest for me to go in and provide feedback on. So I'll try to do it by the end of this week, and then you'll have everything back from me that you need to do the final project report. Remember that the final project report also needs to include some cost estimates. That you haven't done anything related to that yet. It's just a matter of, once you've finalized your pipe optimization, multiplying the number of meters of each pipe diameter by their applicable cost, and then also finding the cost of the reservoir using the linear interpolation between the sizes that I gave. So yeah, you should be in good shape for submitting that final report. Okay, so we're talking about hydraulic jumps today and rapidly varying flow. Here's an illustration of rapidly varying flow that was caused because water was going down a spillway at a very fast velocity. The spillway is so steep that flow is supercritical. Yeah?
Is the project due on Monday or Tuesday? Because it says Monday in the project handout.
The project is due So here it says Friday the 25th. Is there some place where it says other than that? You're saying the handout itself?
Yes, on the handout it says April 15th.
I apologize for that. It's not due on April 15th. So that was probably just a carryover from previous semester. Let's see. And then what does it say on Blackboard? Because there's also due dates specified on that, right?
I did not check them on Blackboard.
Yeah.
It's not posted.
Monday, April 15th. So the 15th? No, that's a mistake. It's not the 15th. What does it say on Blackboard?
It's not posted yet.
No. Okay. It's due on Friday, April 25th. That's the deadline. And I'll go in and fix this and then also make sure that the deadline is correct on Blackboard as well. Are there other questions? All right, so rapidly varying flow. The hydraulic jump downstream is formed because this slope is not steep enough to continue to maintain supercritical flow. This is what's called a mild slope, and so it goes through a rapid variation. And so rapidly varying flow is when there's a transition from supercritical to subcritical flow. It can't keep going supercritical if you've got a shallow slope. And conservation of momentum says that the transition is going to be rapid. There can't be like a smooth change in flow depth because for us to maintain the same amount of momentum, we have to immediately go to a different depth. And so the way we use this momentum function diagram is starting off at the supercritical depth, then encounter the momentum function, and conserving momentum means that there's some sequent depth that has the same amount of momentum, and the new depth is just going to simply be the reflection off of that momentum curve onto the vertical axis, which is the depth. So that's kind of a recap of what we talked about previously when it comes to hydraulic jumps. And we can identify what is the new downstream depth using this graphical approach that I just illustrated. That is, we can generate a table of various depths. What would be the cross section of the flow at that depth? What's the depth to the centroid h bar? And then calculate the two components of the momentum function, the dynamic and the static, and then combine them together. And so to find out what's the new depth downstream with this graphical approach, what you do is you'd start with your original depth. So here it's saying if your original supercritical depth was 0.6, then you'd find out how much momentum is there at that depth, and then finding what is the depth that has approximately that same amount of momentum. And so we could do goal seek and let y change until the momentum is equal to what we knew we had that momentum amount with the original upstream supercritical depth. So there's a graphical method to do it, and there's also this Belanger Momentum Equation where you can numerically solve for the downstream subcritical depth after the hydraulic jump using either of these equations. And it's kind of the same thing where we can either use the Froude number upstream, or we can use the ratio of the critical depth to the upstream depth. Notice though that this term is cubed, whereas what we're doing with the Froude number is squaring it. So either way, what we use this equation for is to say we know what is the supercritical depth prior to the hydraulic jump. We want to know what will be the same amount of momentum, what depth is associated with that downstream. So this momentum equation has some simplifications that will never be true. So this equation really, it only approximates the downstream depth. It's never going to, in the real world, be exactly this, because this equation assumes that when the water's flowing along, it has a uniform velocity distribution with depth. So it's going through a hydraulic jump. What it assumes is that the velocity at the surface and the velocity at the bottom are exactly the same. And that's not true. I mean, what we know from the no-slip condition and what we know from the fact that shear stress is applied by the bottom of the channel is that in the real world, the velocity is fast at the top and slower at the bottom, and there's kind of a velocity profile. So this equation doesn't have that level of sophistication to account for a velocity profile. So that's the first way that this equation is inaccurate, is it doesn't directly account for shear stress or energy loss as you're going downstream prior to the hydraulic jump. It also assumes hydrostatic pressure distribution. That's not so big a deal as the first assumption, but it's not great because what it's assuming is, that delta H is equal to delta P is equal to gamma times delta H. So if we go down through the fluid, the Belanger Momentum Equation assumes that the pressure is described exclusively by hydrostatic equation, when in reality, anytime the water is moving, the change in pressure is affected by the velocity of the flow. And then it's also assuming that the bed is horizontal. And in the real world, generally there will be some downward slope. Again, that's a relatively minor issue for a lot of applications if you have a relatively small bed slope. But any deviation from these assumptions is going to introduce some error in what this predicts as the actual downstream depth and what you'd observe. So I just wanted to make you aware of those assumptions. So we can still use this equation, but it's not always going to be 100% spot on. So the same approach allows us to estimate how much energy is lost in the jump itself. Because one of the main purposes of a hydraulic jump when we induce them to occur is to dissipate energy. Some hydraulic jumps are naturally occurring. Like if you're going river rafting and you notice a standing wave, that wasn't put into place by a person. It's just a result of an abrupt drop in elevation and supercritical conditions followed by subcritical conditions, and the standing wave forms because of that. But there are cases like downstream of spillways where we induce a hydraulic jump specifically to get rid of extra energy, because we don't want a bunch of additional velocity and energy scouring the channel and causing erosion and carrying sediment downstream. And so hydraulic jumps can be very useful in dissipating energy. There's just a lot of turbulence and countercurrent flow in the section of the hydraulic jump. And so this formula estimates in units of meters, so delta E is expressed in units of meters, how much energy is lost when you go through a hydraulic jump and have the upstream depth Y1, the downstream depth Y2. So this is just showing that if you want to understand the amount of specific energy that is lost, you can use this equation. And so we're assuming momentum is conserved through the hydraulic jump, but specific energy is not conserved through a hydraulic jump. You could lose more than 50% of your energy through a hydraulic jump, potentially, and that can be a good thing. So there's a mild slope that's forcing the hydraulic jump. And by the way, the hydraulic jump doesn't always, it's not always extremely visible like this. This figure is showing that sometimes the hydraulic jump could be drowned. This is an illustration where the hydraulic jump is still there, but there's some feature downstream that is causing the water downstream to pool. So like maybe we've got an extra obstacle off the screen here that we don't show, but it's forcing the water level higher. Or it could be just that maybe this material is really rough or it's not much of a slope. But for whatever reason, the tailwater, the water downstream of the hydraulic jump, the water's moving slowly. And so the water backed up and it drowned the hydraulic jump. And we'll see that. We're going to go back into the lab, I think probably on Friday, just for a few minutes. I'll set up the hydraulic jump in the lab and we'll play around with the slope to see how that changes the location of the hydraulic jump. We'll play around with the tailwater and show how that can drown the hydraulic jump. But the point is that the hydraulic jump isn't always as distinct and visible as is shown in this first upper illustration. Sometimes you may not even know that the hydraulic jump is there if the tailwater is high. And actually, it's a bit of a dangerous thing. Sometimes kids will swim around in canals in places where they have like open ditches for irrigation. And this is a little bit like a rip current that could pull people down into the water. So there's some information online about the risks of hydraulic jumps in irrigation systems, because if they're invisible and they are pulling people down under the water, then it can be a drowning risk. So we created a momentum depth diagram using Excel in class on Monday. Some of you watched, some of you followed along and calculated it. The video's there if you didn't actually do the calculations yourself, but conjugate depths, or sometimes they're known as sequent depths, are those depths that have the same amount of momentum. Upstream with the lower sequent depth is supercritical. Downstream with the higher sequent depth is subcritical. And the same characteristic is true on a momentum depth diagram as on a specific energy diagram, that the point that's furthest to the left, which is associated with that minimum, is associated with the critical depth. And so this critical depth is the dividing line. And then the further away you are from the critical depth, the more dramatic the hydraulic jump is going to be, the more energy that's dissipated. So if your original upstream depth is almost critical, like it's just barely less than critical, then the hydraulic jump is not going to be very dramatic. If it's close to critical already, it'll jump up to another depth that's approximately critical, and there's not going to be very much energy dissipation. So the big energy dissipation is when you have a big change in elevation from upstream to downstream. So when you have a very small Y1, it'll jump up to a very large Y2. And therefore, if Y1 and Y2, if the difference in depths is large, then delta E is going to be big. So you dissipate more energy the larger the difference between the upstream and the downstream. Okay, so let's go through this example together. Let's say this is a rectangular channel, which helps us to calculate things like the Froude number. It makes the Froude number easier to estimate. Let's say that this channel's 9.4 meters wide. The upstream depth is 0.86 meters, and it's carrying 123 cubic meters per second. So this is a big river. We got a lot of water moving here. And let's find out what would be the downstream depth by using this Belanger Momentum Equation, and then also estimate the fraction of the initial energy lost through the jump. So what that means by fraction is, it means calculate delta E and compare that to E1. So we're going to have to calculate both E1 and also delta E in order to find the fraction. Okay, so I'm going to pause, give you a chance to play around with calculate the Froude number, put it into Belanger Momentum Equation, and find Y2. Okay, so if we know the width of the channel is 9.4, and we know the flow rate, and we know the depth of flow, that gives us everything we need in order to determine the Froude number upstream. And by the way, if the Froude number upstream is anything less than 1, there's not going to be a hydraulic jump. There will only be a hydraulic jump if conditions are supercritical upstream. So what we're expecting to see is a Froude number greater than 1. So putting it into this kind of generalized equation here, we could do it in terms of flow per unit width since it's a rectangular channel. We get the same answer whether we use that flow per unit width equation or the more generalized equation for Froude number. But the Froude number is 5.238. So it is supercritical at 1. And if we put that into the Belanger Momentum Equation along with the upstream depth, then what we should see is we're going to encounter a downstream depth of 5.956 meters. So it's really going through a dramatic change in depth. It's going from less than a meter to almost 6 meters. So this is going to dissipate a lot of energy through this hydraulic jump. So any questions so far in calculating the Froude number or using the Belanger Momentum Equation? Okay. So next, for determining the energy loss, we put it into this formula for delta E. And so what it tells us is that we're going to lose 6.56 meters of energy through the transition. And so we need to know how much specific energy was there originally at 1. And it's going to be the depth plus the velocity head. And so you can calculate the velocity head any number of ways here. I determined the V at 1. Since we already know the depth and we know the flow rate and the width of the channel, we can find V1. So energy-wise, there's going to be 12.659 meters of energy originally at 1. So the fraction of that initial energy which is lost through the transition is going to be delta E divided by E1. So how much of the energy was lost as a fraction is the 6.456 meters that was lost divided by how much was initially there. So that's about 51% of the specific energy that was originally present. So the other way we could have found out how much energy is lost is just to find E2. Because we know the new downstream depth, right? It's 5.956. And so E2 would be Y2 plus whatever velocity head there is. And it's still the same flow rate. The Q in and the Q out of the hydraulic jump is the same. So this flow rate of 123 cubic meters per second, that's the flow rate upstream and the flow rate downstream. So you can use the delta E formula, or you could just find E1 versus E2. The change is the delta E, and then divide it by the initial specific energy upstream prior to the jump. All right, so that's your first exposure to the Belanger Momentum Equation. I think between the demo with Excel and having this equation in your hands enables you to solve homework 11. I think that's basically all of it. There's always a twist, though, so let's talk about trapezoidal geometry, because depth to the centroid is negligibly easy if the channel is rectangular. We talked about this on Monday, how if the channel is rectangular, then the depth to the centroid is just y divided by 2. But if it's a trapezoidal channel, then the depth to the centroid isn't just the flow depth divided by 2 because of this extra area on the left and the right-hand side of the trapezoid. So here's a generalized formula for the distance from the bottom up to the centroid. So delta H is the distance down from the surface to the centroid. So we can use this figure and this this formula to find where is the centroid, but then we kind of have to reverse it since this is measuring upward from the bottom and we want to know downward from the top. So let's put it into this specific case where the bottom of the channel is 3 meters wide, where we've got 1-to-1 side slopes and so on. Let's actually find out if it's 1 meter deep, what is the depth of the centroid in this case. And so first of all, let's determine the area. We don't even necessarily need to calculate the area. Let's just calculate capital B here is the top width. And so you can see if it's 1-to-1 side slopes, then that means we're going to have, for a meter of depth, 1 extra meter on this side on the left for the top width, and then 1 meter on that side. And so capital B is 2 meters plus 3 meters, so it's 5. 5 meters across the top. And so the distance up to the centroid is going to be, so distance is y plus y times 2b plus lowercase b divided by 3 big B plus little b. All right, so y, the depth of the centroid, the flow depth is 1 meter, 2 times the top width of 5 meters plus the bottom width of 3 meters divided by 3 times 5 meters plus 3 meters. Okay. So if we do that calculation, then what we're going to get is that the distance from the bottom up to the centroid, y, the distance up to centroid is 0.5417 meters. So then if it's 1 meter from top to bottom, and we have to go more than halfway to get to the centroid, then it's going to be less than halfway from the top downward to the centroid. So here it is, yeah. So h bar is going to be 1 meter of depth minus the distance from the bottom to the centroid, so it should be 0.4583 meters as the depth from the surface to the centroid. So that's what you need to have in order to graph the momentum function in a trapezoidal channel. And if I remember correctly, the reason why I'm telling you this is because you have a trapezoidal channel that you need to create a momentum depth diagram for. So in that case, which I think is in the homework, you'll need to use this equation to find the h bar. Any questions about how to find h bar in a trapezoidal channel? And this gives you how to find the area in a trapezoidal channel, which you're going to need that because the momentum function, the static component of the momentum function is the area multiplied by h bar. So now you've got the formulas for both what is the area and what is the distance from the bottom to the centroid. And so h bar would be y minus this distance. So h bar is y minus distance up to centroid. This is the generalized formula. All right, so I mentioned we're going to go look at the flume in the hydraulics lab in a future class meeting, and when we do, we're going to kind of control where the hydraulic jump occurs. And the analysis for finding out where the hydraulic jump sets up, the way it's laid out in the book, it uses some new variable definitions that we haven't encountered before. So I want to help you to understand what those variable definitions are that are used in the book. So previously, you saw like y prime 1. Do you remember when we had pooling upstream of some obstacle, and that was called y prime 1? Well, your book uses that in the section related to hydraulic jumps to talk about the conjugate depth of a hydraulic jump. So in other words, the Belanger Momentum Equation, which I just showed you, Y1 is upstream, Y2 is downstream. Well, when we're talking about locations of hydraulic jumps, then the book uses this new Y prime one to talk about the conjugate depth downstream of the hydraulic jump. And then Y2 is the normal depth for the channel downstream of a hydraulic jump. So just a bit of a warning that there's some new variable definitions. Really, the heart of this assessment of where is the location of a hydraulic jump is evaluating what is the capacity of the channel downstream of the hydraulic jump. So, you know, the channel that the hydraulic jump is occurring in, what are its characteristics like the Manning's end value, its roughness? What's the slope of that channel? And having an understanding of the geometry, the slope, the roughness, allows you to predict what's the normal depth downstream. So how much water can be accommodated for a given depth in the channel downstream. And there is a way to graph that, you know, flow depth versus flow rate, Q. So depth versus flow rate. We can make a rating curve for the channel, but you can also express the hydraulic jump in these same terms with what would be the jump depth for a certain flow rate. And ideally, you would have an immediate hydraulic jump right after whatever's causing it. So here you can see it's an underflow gate that's causing the hydraulic jump. The fact that we've got this gate mostly closed, and so here's the critical depth. This dashed line is associated with the critical depth, and so we're forcing the water to come out from under the underflow gate here at a depth that's less than the critical depth. And so it's super critical. It's going to have a lot of velocity because of all the pressure that's built up behind the gate. So the water's flowing out super critical, but it's a mild slope, so it has to jump. Ideally, it would jump immediately after it goes through what's called a vena contracta. That's where, you know, the velocity is continuing to increase a little bit just after the water exits from the gate because of all the pressure that's behind the gate. And so therefore, the depth is decreasing even a little bit more. But then as soon as it reaches this lowest point, it immediately goes through the hydraulic jump. And ideally, the hydraulic jump downstream, which the Belanger Momentum Equation calls Y2, is the same as the depth that that flow rate would cause in the channel downstream. Now that isn't always going to be the case because usually the channel is either going to be more steep or more shallow than the depth that is the sequent of what your supercritical upstream depth was. And so here is an example of a downstream jump. And this is pretty common. What you'll see most of the time where they're forcing a hydraulic jump to set up someplace is that you'd want it to set up away from the gate or away from the spillway. And the way that we can understand this is that there's a period of gradually varying flow. So the water is just increasing a little bit, and then eventually it gets to some depth that is the match of the normal depth for the channel. So if we start on the far right-hand side, this channel has a certain slope, and it's carrying water at a given depth for the flow rate that we're putting through here. So Y2 in this figure is just the normal depth downstream. And because we've got this gate closed pretty tight, it doesn't immediately have to transition through to its hydraulic jump status. Like it's gradually increasing depth as it's losing velocity. and it encounters the hydraulic jump when this y'2 matches the sequent of the normal depth downstream. So here, the hydraulic jump has a rating curve that's above the tailwater rating curve. And when that's the case, when the jump rating curve is above the tailwater rating curve, then the jump is going to move downstream until the water depth increases and matches. So here y'2 is going to be the sequent of the normal depth downstream. So the water out of the gate continues to rise until it's the conjugate of the depth y2, which is the normal depth based on the channel characteristics downstream. So the opposite of this is that the jump moves upstream rather than downstream. So just to set the stage, this is kind of the perfect hydraulic jump, jumps immediately. It can either do this, or the jump can be further away from the gate or closer to the gate. So for it to be right after the gate, then the tailwater curve and the jump rating curve are on top of each other. And what that means is, it just means by coincidence that the normal depth downstream equals the conjugate depth of the hydraulic jump. So this case is if the jump is further away from the gate, and that happens when the channel carries more flow than that first case. In this first case, this slope was less. This slope is more, so it's still a mild slope, but it's a steeper slope. And so if the slope is steeper, then y2 is less. And so the water depth has to increase a little bit to find that lower sequent. So then this is the opposite case of it running away from the gate, is that the hydraulic jump actually moves upstream, approaches the gate, and the hydraulic jump will be drowned here if the jump rating curve is less than the tailwater rating curve. And so what this means is that for a certain flow rate, think about if you're going to draw a vertical line up from the horizontal axis. For a certain flow rate, the tailwater needs more depth than the hydraulic jump does. So this is the y' one, which is saying after the hydraulic jump. So for a given flow rate, if the tailwater depth is larger than the hydraulic jump's depth, which is required, then the tailwater is going to drown the hydraulic jump. So you won't see the hydraulic jump. It's still there. This dashed line is just showing that the hydraulic jump still exists, but it's submerged in the tailwater. So we'll see that, and hopefully it'll continue to make more sense when you actually see the relationship between slope and the hydraulic jump location and the depth. So we can either use the Belanger Momentum Equation, or we can graph the momentum function, and the critical depth is the furthest to the left, the minimum momentum. So what's the critical depth here in this case? It looks like it's about 0.6, 0.7, 0.8. If we're going to just find this far left point, it's about 0.8 meters. So if the original upstream depth is 0.6, then the same amount of momentum is going to be associated with about 1.05. So this is showing the span of the hydraulic jump. If the initial upstream depth is pretty close to the critical depth, then it's barely supercritical, and it's going to be a small jump height. But then if you had an original depth of 0.3, we take it over and up, that's going to be a much larger jump in depth from the upstream to the downstream of the hydraulic jump. So the smaller the y1, you'll have a larger Froude number. And if you've got a big Froude number, then the ratio of upstream to downstream is much more extreme. So our book steps through different types of jumps depending on the Froude number. A low Froude number jump is called an ungular jump, and you can see kind of these flow patterns are leading to rippling at the surface. A weak jump is from a Froude number of 1.7 to 2.5. And there are likewise some eddies and rollers on the water surface where you're beginning to actually maybe see a little bit of white water in a weak jump. An oscillating jump is considered to be pretty undesirable from an engineering standpoint because some of the velocity vectors are coming down and encountering the bottom of the channel. So it can lead to scour. An oscillating jump is undesirable, but a stable jump is maybe the most advantageous because it dissipates a large amount of specific energy, which is good to prevent scouring, and none of these velocity vectors are pointing down towards the bottom of the channel. So there's a large rise in the water level, dissipating a lot of energy, and it's not destructive. And then when you go beyond that stable jump into the strong or rough jump, then you'd need to have a ruggedized stilling basin to dissipate that much energy. They generally not rely on a gravel or soil channel. They would armor it with concrete. Okay, so we're done for today. When we get together on Friday, we'll talk just a little bit more about hydraulic jumps. I hope that we'll take a brief field trip down the hall to the hydraulics lab. So I'll see you for that on Friday.